All right, this is going to be the video for differential equations, section 7.3, day 2, which is about something called the unit step function. This will be much more straightforward than, less complicated than yesterday's topic and tomorrow's topic, but we do dedicate a whole day to it just because it's a different way to think about something. Once you get how it works, though, it's really straightforward, but it is a little unusual at first. So this is a very short video to explain how this works. We're going to define a unit step function will basically allow us to turn on and off other functions for right-hand sides at specific points in time. All right. And it's the kind of thing that you just have to try some homework and practice with. So we have a variety of problems for you to try things and see how it works. Let's say the Laplace transform is particularly useful in solving differential equations where the right-hand driving function is piecewise defined with abrupt changes in behavior, because it's hard to do things with derivatives when we don't have continuous functions. We can model functions in time which change behavior abruptly by using this thing called the unit step function. So the unit step function is this. It's with a lot of times the book will use a kind of a cursive U. I'm just going to use a U here, but you might see it written in a fancier U for unit step function. T minus a, where a is a constant. And what that means is it's a function which stays 0 as its output until a certain point time t equals a, at which it immediately jumps to, and at that point and further, it has the value 1. Right? So it's 0 up until a point in time, and then it's like a switch. It turns on and becomes a 1 from that point on. And it is a 1 at that time and later. Okay. It's also not defined for negatives. So this is usually used in situations where we're modeling situations where the independent variable is time and where negative time would be undefined. So technically the unit step function starts at t equals 0, so you don't have to do anything to deal with the fact that there's negative time. There is no negative time. The unit step function starts at time is 0, like you would expect in real life. All right, so how is this useful? Well, let's say you have some other function, and maybe it it is defined for t from negative infinity to infinity, but you want to cause everything to start at a certain time. So you want to see nothing of this function until you get to a certain point. You just want to take the function as it's going through time and just flip it on. So it starts, there's nothing, and then it just starts. All of a sudden, the function matches at that point. Well, the way you do that is you take the function, and now if we want that same function, this actually is shifting in time. So you can cause this to start at a new time. So this is more than just turning it off, on and off at a certain time. I want this point, which was at t equals 0, to slide up here to be at t equals a. So we're actually shifting this function over in time to start here as if this was t equals 0, but now it's at t equals a. So the first thing we do is, if we don't take f of t, but we take f of t minus a, that means that t equals a functions as 0, so that's the right shift in time. But then if we don't want to see anything of that function prior to that time, we can multiply this f of t minus a times the unit step function t minus a, so that it forces the amplitude to be 0 before that point. And that means the total function f of t minus a times unit step function of t minus a will be 0 up until this, and then it'll turn on and it'll begin with whatever this would have been at t equals 0. So effectively turns on this function starting at its starting point, but moving everything over to starting at t minus a. So this allows us to turn on and shift a function in time. Okay. Another thing you can do is you can cause a function to turn off. Maybe a function has been going for a while, and then you want the function to stop at a certain point. Okay, so here's a function. Okay, and here's a unit step function at time t equals a. Okay, now if I just take the original function f of t, and then I multiply by unit step function at t minus a, that means we take the unshifted function, but we just have it start applying at this time. So it's like this part of the function is ignored, and we don't see any of this function until here. We just turn, the function's going along, but we force it to be not applied to the system, and then we allow it to apply starting here. So if you take an unshifted function and then you multiply by the unit step function at a certain time, it just takes the unshifted function and turns it on. Now, what if we want that to be applicable for a certain amount of time, but then we want it to turn off at a certain time, right? So what you could do is say, all right, take that same exact structure and add a negative copy of it. If you add a negative copy of it, right, then it will subtract back to 0 at that certain point, right? So if you were to take that same thing, okay, and add that to the original function. So if I take the original function f of t and I take a negative of the f of t but shifted in time and add that, then you're getting the original function. But in this, starting at this point, you've got this function plus the negative summing to 0. And so they sum, those two things, this negative and positive, sum to 0. So the result is that the function turns off at a certain point. So if you take an original copy of a function and then you subtract a copy of the same function but multiplied by a unit step function, it effectively turns off the function at that time. Okay, so you can do a lot of things with this unit step function. You can cause it to shift over in time by taking a time shifted version of the function, multiplying by this to allow it to not start until that time. Or you can take an unshifted function, subtract a negative version or subtract a copy of it, but just starting at a certain point in time so that you subtract itself starting from then on and force it to 0 to turn off the function. And then you can combine these different effects in different ways. So for example, you could do something like this. You could say, let's take the unshifted time function multiplied by um, uh, the unit step function at t minus a, which means that this forces this amplitude to be 0 until we get to t equals a. And then let's take another copy of that function, but subtract it after the point b, which means that the function's allowed to go for a while, but then starting here, a negative version of this is subtracted back off to force this to a 0. So this particular structure, which allows a shifted on minus a shifted off, allows you to get just a piece of the function within two time limits here like this. And you can get different effects too. Right, so that's just with those three examples, that's all I'm going to show you here. That should be enough for you to play around with the homework problems. The homework problems are going to ask you what combinations of either shifted or unshifted f functions and shifted unit step functions will allow you to produce the wave shapes. And it's the kind of thing you just have to practice. So we're going to have problems tonight just related to practicing using the unit step function. So give that a try.